All right, let's go ahead and get started. How's everybody's long weekend? Not long enough. What do you do for work? What do you do for work?
I'm a server.
Cool. What's that?
That does not sound fun.
Yeah.
I work 50 hours. Oh, well, that's
Well, making money. Yeah. Did anybody do anything actually fun?
I went to my boyfriend's lake house with his family.
Nice.
Yeah, that was nice.
Where is the lake house?
Scottsboro.
Yeah, it's a lake house. That's awesome. Fantastic. All right. Before we get started with what we're going to be covering today, if I can get this mouse freaking working. All right. Bear with me here. Need to move y'all. So for those of you who don't know, Excel is wonderfully powerful and does a lot more than what y'all have probably experienced so far. As you're going through and practicing, there's kind of a predilection to want to get more data, right? To practice on more data, but it's tough sometimes then to evaluate whether or not your answer is correct. And so I'm giving this to you because you can use these equations, these macros in Excel to calculate the actual answer for you after you've worked it out by hand. Now, where you see these parentheses, that's where you have to select all the data, right? And so if you want to get the sum of squares, type in equals dev square, open parenthesis, and then select the entire data set that you're interested in. And then you'll see things with like variance, so var, and standard deviation. You have .p or .s. Older versions of Excel I don't think give you that option, and I don't know what the default is. But when you're typing it in, you'll see stdev, and that's an option, and that's the older version. But you want to make sure you're selecting the correct one, either the sample or the population. And then simple things like square root, SQRT, and then sum, add them together. Yeah.
Did this work on Google Sheets, whatever it's called?
I never use it. I've used it a couple times, and I'm almost positive it's a very similar naming structure. I would try that. But if not, you at least know what to say, you know, var.p equivalent in Google Sheets and see what pops up, because there's inevitably a list of that if there's a difference. Yeah. And I think these do work for Apple numbers as well. Any questions about that? Cool.
Are these the only ones we're going to use? All the equations?
No, but these are just what you've got so far. And this, I'm not going to give them to you throughout the semester, but you know that you can go look for them. So if you're looking for like an ANOVA, Excel is going to have something that'll calculate the ANOVA for you and calculate that stuff. So this is just to serve to highlight the fact that you can use Excel or Google Sheets or Apple numbers to give you the answer if you want to be creating your own practice problems. All right. So, what did we learn last time? Okay. That was the time before that. I mean, we covered it again, but okay. And what is standard deviation? Yes. And when you say standard distance, what is that standard referring to? Standard for what? Yeah, it's essentially like the average distance from the mean. Exactly. So it's standard because it's essentially taking the average distance for every individual data point and saying, okay, this is the distance there.
Like the positive and negative leaning or whatever?
Skew.
Yeah.
Mm-hmm. Yeah, so if I draw data that looks like this, is that positive or negatively skewed? Positive, exactly. The tail points in the direction of that skew. All right, what else do we learn? Yeah, how to calculate the variance. And so what's the relationship? How do you get the variance once you have the sum of squares?
Variance divided by n.
Yeah, exactly.
Or sum of squares divided
Yes,
by
I'm
n.
sorry, I did. Somebody was speaking up? Yes, exactly. So it's divided by n for the population. For the sample, what is it divided by? N minus 1. Exactly. We call that our degrees of freedom. And then what's the relationship? How do you get the square root from the variance? Or excuse me, I just give you the answer. How do you get the standard deviation from the variance? You take the square root of the variance. Yes. Well done, Nate. And who, off the top of their head, remembers the equation to get the sum of squares?
Sigma of x squared minus sigma of x n squared divided by n.
Exactly. Yeah. So when we look at this equation, we have sigma x squared represented here on the left. And somebody else, what is that telling us to do? Yes, exactly. So you want to square all the numbers, every x, square that x, and then add all of those squared values together. Then you're subtracting. What does this tell you to do over here? Exactly, yeah. So you take the sum of all the x values, all the data points, add them together, and then you square that summed value, and then divide it by n. Exactly. Questions about what we covered last time? Awesome, awesome, awesome. All right, we are rocking and rolling. Here is your fun fact of the day. Reed Hastings has said that he was inspired to start Netflix after a $40 late fee on a VHS copy of Apollo 13 was accrued. How about that? I always love those kind of like butterfly effect things. Okay, what if there even was no Apollo 13? Would we then have no Netflix?
Or what if he turned in his VHS copy on time?
Yeah, or what if he decided to just not go to Blockbuster that night? Yeah, exactly. That's pretty cool.
I mean, we just have to live.
The worst. Just kidding. All right. So today, we're talking about z-scores. Z-scores are really helpful in that they allow you to standardize data sets. So we will answer this question at the end of the class today. Well, let's say we have two different cities, Caribou, Maine, and Boston, Massachusetts. And Caribou, Maine gets on average 110 inches of snow every year with a standard deviation of 30 inches. Boston, on the other hand, let's say gets an average of 24 inches of snow a year and has a standard deviation of 5. And then let's say we got the snowfall totals for both Caribou and Boston last year. And Caribou got 125 inches and Boston got 39. And we want to be able to answer in which city was the winter worse compared to baseline for the citizens? Well, we'll answer it in just a minute. Yeah. But you're right. That's the answer. And you know why it was worse in Boston?
Because 110 plus 30 is like the standard deviation. That's more than 125.
No, it's because where the Patriots play, and God hates the Patriots. That's the answer. All right. But you're also right about that. Class over. Ace will just help tutor you on everything you need to know. And so you can see why this may present a problem, right? Because you could say, well, Caribou got 125 inches, and Boston got 39, so Caribou's winter must have been worse. But if we're comparing against baseline, we also know Caribou got more snow in general on average. And we need to compare against that baseline. And so by itself, a raw score, or as we call it, an X value, right? Seen the X notation repeatedly, provides very little information about how that particular score compares with other values in the distribution. Z-score, on the other hand, tells you exactly where that score is located compared to every other score in the distribution. All right, so if I wanted to get the average height of a UAH student, I could do that. I could get the distribution of everybody's height. And then I want to see how tall I am compared to everyone else here at UAH. So let's say the mean height was 5 feet 8 inches tall, and I'm about 5'10". Well, it tells me I'm slightly above the average, but I don't really know what that means for how many people I'm taller than, how many people I'm shorter than, and where I fall on that distribution. By converting all of that to z-scores, I can then know definitively where I am in relation to all the other folks here. And so we've already talked about central tendency, right, with mean, median, and mode. We've talked about variation or variability, standard deviation. And we've talked a little bit about shape, right, with the normal distribution. So about what percentage of people fall between -1 standard deviation and +1 standard deviation from the mean? Yeah, about 68%. So once we've got our central tendency, right, we have that mean value, and we know the variability of that data set. We know what the standard deviation is for that data. And if we know that the data is normally distributed, right? So we have a symmetrical bell curve here. You could flip the left and right over this middle line, and it would look the same. So once we have that information, we change that X value into a Z-score, creating a signed number. So when I say signed, I mean positive or negative, called the Z-score. And the Z-score will have that positive or negative. It will also have a numerical value. So closer to 0 means it's closer to the mean. The higher the number, either higher positive or more extreme in the negative, means it's further away from the mean. And so you'll get something like this here. So this means you've got a z-score of 2. And as you'll see in just a second, what this means is for somebody whose z-score is 2, positive 2, they are 2 standard deviations above the mean. So if we look at these 3 graphs, up top is what we looked at last time, right? So we've got our standard distribution here, this curve. We have our mean, represented by lowercase mu. We have our standard deviation, represented by lowercase sigma. And what you have here on the bottom is the z-scores. You can also think of these as being representative of the standard deviation. Right? It's the number of times that standard deviation goes in. So if we look at the bottom left here, let's again say we have IQ with the mean of 100, and we have a standard deviation of 10. We know that 68% of people will fall between 90 and 110. And so that's descriptive. But now we can convert all of that to the z-scores by saying 100 is now 0. Positive 1 standard deviation, so what was 110 for the score is now a z-score of 1. 120 is a z-score of 2. 80 is a z-score of negative 2. Everybody with me so far? Cool. So to get the z-score, we use this equation. So what is x?
The score.
Yeah, it's just every individual data point, right? So again, I'm going to just keep rehashing this when we see the various letters. So x is always just a signifier of a data point, the data point of interest. What is the lowercase mu here? Yep, mean, exactly. And what is the lowercase sigma again? Standard deviation, perfect. So what this equation is saying is to get your z-score, you take the x, the value that you're interested in. From that, you subtract the population mean. And then you take all of that and divide it by the standard deviation. Right, so let's do that with our data back here. So we want to see what's the z-score for a population of, 120, when the population has a mean of 100 and a standard deviation of 10. So our z is equal to 120 minus 100, which is that mean, divided by 10, which is that standard deviation, or 20 over 10 equals positive 2.0. So somebody with an IQ of 120 in this population we pulled from has a z-score of positive 2.0. All right, so let's work out an example. Assume that the mean of the first statistics exam was a 78 and the standard deviation was 10. What would be the z-score for somebody who got an exam score of 93? So let's write this down. The mean was 78. Mean 78. Actually, I guess I should make that mu, excuse me. Is 78. The standard deviation was 10. And we're interested in the exam score of 93. So our x is 93. So we take that equation, z equals x minus mu over standard deviation. So z equals 93 minus 78 over 10, or 15 over 10. So the z-score for somebody with an exam score of 93 is 1.5 in a population where the average score is 78 and the standard deviation is 10. Make sure we did that right. Yep. So, yeah. So what that's translating to is somebody who has an exam score of 93 in that population is 1.5 standard deviations above the mean. Yeah.
So we're going to be working with decimal or not?
Yes. Yeah, I think that'll probably be the easiest. If we were doing the exams in person, I would say it doesn't really matter, but I think for the purposes of the exam, doing decimals would be easiest to standardize to get. Yeah.
When the answers are positive, do we need to put the little plus sign?
You don't really have to, but it's kind of the practice.
Okay.
So.
Like some like online like math stuff like math Excel, we don't clear exactly
Yeah.
how it wants it to knock you down.
Yeah. When I'm writing the exam, I'll try to account for that, but if I forget, I'll just go back and regrade. So, yeah. Yeah. Yes. Yes, of course. Yes, for those listening, to reiterate, we'll be using Lockdown Browser and Respondus Monitor. All right. Any questions about the example we just did? Oops, I'm seeing some questions coming in that I'm not. When's our first test? The 23rd. Yeah, thank you. Any questions about what we just covered? All right, pretty straightforward. So the nice thing about this is we can also give you a z-score and have you figure out what's the x value which corresponds to that z-score. Right, so if we just take our z equation from before, where is it? Our z equation from before, and we want to get the x, we add mu to both sides, and then we multiply by sigma, and that gives us this equation here. So to get the x, we take the standard deviation, or excuse me, we take the mean, and to that we add the standard deviation times the z-score. And so as you'll see in a little bit, this allows us to translate data from one scale to another. Right? So it's very unlikely when the IQ test was first developed that it had a mean of 100 and a standard deviation of 15. Right? But by taking this approach, you can now make it much easier to interpret by translating every one of those data points to get the desired mean and standard deviation based off of those z-scores. So, again, let's assume that the mean for the first statistic exam was 78, and the standard deviation was 10. What would be the raw score corresponding to a z-score of 2? So again, let's go ahead and work this out. Your mu is 78, your standard deviation is 10, and your z-score is 2. So we'll take our equation to get x. We're solving for x here. We want to take the mean plus your z-score times the standard deviation. My z's kind of look like my 2's. So highlight that there. All right. So we take 78 plus z-score of 2 times our standard deviation of 10. And order of operations, what do we do? Yes, we multiply. So we get 78 plus 20, or 98. So somebody who is 2 standard deviations above the mean got a 98 on their exam. Yes, exactly, William. Good job. And so you can see how this is helpful. If you know that 97.5% of people fall below 2 standard deviations above the mean, somebody who got a 98% on their exam is coincidentally in the 97.5 percentile, the 97th percentile. We can round up to the 98th percentile. Doesn't always work out like that, but it just so happened it did on this one. Make sure we did everything right. Yes, we take our x, we grab our population mean, we add our z-score times our standard deviation to get our x value. Questions about that example?
I have a question about the z-score.
Yeah.
Wait, so what is it? I mean, I know you've been saying this, but what is it actually telling us about the data? So if the z-score ends up being +2, is that like literally what does that mean?
It's the number of standard deviations away from the mean. So if you have a z-score of 2, that means you are 2 standard deviations above
The mean. Okay.
Does that make sense?
Yes. Thank you.
Yes, exactly. Any other questions? Exactly, Amber. Good job. Awesome. Awesome, awesome, awesome. So again, just to reiterate, The z-score is just telling you the number of times you have to multiply by the standard deviation to get to your value above the mean. So if I want to get to a score of 115, what would my z-score be here? 1.5, exactly. Yeah. Yeah, this is actually easy because your standard deviation is just 10, as you can see here. You've got your mean of 100. Yeah. Extra easy. What would a score of 95 be? Yes, minus 0.5, exactly. Easy peasy. We're rocking and rolling now. So remember, the mean is at z equals 0. And the extreme tails correspond to roughly about -2 and +2. So at -2 and +2, you are including about 95% of the data. So if we go back here, -2, +2, you've got about 95% of that data included between there. Cool? So the fact that z-scores identify the exact location within a distribution of that score means that you can use z-scores as both a descriptive statistic, so a statistic that's telling us about the data, and an inferential statistic, which is giving us probability. All right, so I want you all to work on this problem here. Transform the set of raw scores below into a z distribution, and you're going to have to find the mean and the standard deviation for the raw scores and each of those points. So go ahead and take a couple minutes, and then we will do it together. 32 more seconds. All right, what are some of the things we're going to need before we even do any of these calculations? What are the things we just know we're going to need? Yep, so we're going to need our sum of squares. What else?
Sigma of x.
Yes, the mean, the standard deviation. I'm sorry, what did you say, William?
Sigma of x to find those at least.
Yep. Yeah, exactly. What else?
Variance.
The variance, yeah. So the variance, we'll get the sum of squares. That'll lead into that variance. Whoops. Ignore that. That'll lead into the standard deviation. Okay, so we know we need our sum of squares. We know we need our, actually, we really only need our standard deviation, but to get our standard deviation, we have to get our variance. And to get our variance, we need our sum of squares, right? So let's go ahead and work this out. So we have our x values are 3, 5, 6, 7, 8, 7, 6, 4, 9, 5. All right, so we've got our x. To get our sum of squares, we need the sum of x. We also need the sum of x squared, right? And so 9, 25, 36, 49, 64, 49, 36, 16, 81, 25. So we get our sum of x squared. All right, so somebody who already has it, what is the sum of x? I'm hearing a couple different things.
It's 60 for the sum of x.
60, I think, yeah, I think it is 60. So that gives us the sum of x. All right, what about x squared? $390? Is that what everybody else got?
Yeah, I got 390.
Yep. Okay, 390. Perfect. All right, so to get our sum of squares, we're going to take 390 and subtract 60 squared over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over 10. So that gives us 390 minus 3,600 divided by 10, or 390 minus 360. So our sum of squares is 30. Is that what everybody else got? Cool. All right. So we will take our 30 as our sum of squares. And to get variance, what do we have to do? Yep. So we take our 30 divided by 10, gives us 3. And then to find the standard deviation, what do we do? Yeah. So we take the square root of 3, and that gives us, what, 1.73-ish? Is that right? Cool. All right. So now we've got everything we need to calculate the z-scores for every individual score we've got back here, right? And so let's go create a new one. All right, and so it's going to be 3, 5, 6, 7, 8, 7, 6495, 6495. And these are each of our x values, right? These are just pulled from the beginning. And so to get the z-score, what is the equation again?
X minus mean divided by standard deviation.
Yeah, so it's x minus the mean divided by the standard deviation. And so we know our mean is what? 6. Yep, so you would have had to calculate that in addition to what we just did. And then our standard deviation, 1.73. All right, so for each one of these x values, we're going to calculate its z-score. So for 3, it's going to be 3 minus 6 divided by 1.73. 5 minus 6 divided by 1.73. 6 minus 6 divided by 1.73, and so on. So I'm not going to actually each one of those, but all right. Zoomies, can you still see the PowerPoint now?
Yes.
Couldn't, somebody tried to speak up and it kind of cut out.
Yes, I can still see the PowerPoint.
Okay, perfect, thank you. All right. So you can see when we take that x, that 3 minus 6 divided by the 1.73, is that right? Yeah. And so you can see as you go down here, wherein you have an x value that is equal to the mean, so an x value of 6, your z-score is 0. None of these are really easy off the top of the head here. But so based off of every one of those individual data points, okay, so white screen for y'all. Okay, give me just a second here. How about now?
We can see it.
It's what? I'm sorry.
I can see the PowerPoint now.
Okay, perfect. Awesome, awesome, awesome. All right. So, yeah, you can see for every individual x point, knowing our standard deviation of that 1.73, we just take the x minus the mean, or in this case, 6, and divide it by that standard deviation, and we get all of our z-scores. Now, what happens when I sum up all of these z-scores? Yeah, you should get 0, right? Because this is just talking in a normal distribution about the spread around the mean. And then if it is, in fact, a normally distributed data set, you shouldn't have any problems getting that to average to 0. Questions about that? So one of the things I've noticed teaching stats in the past is people will come across a problem like that, or a problem that we'll get later on in the semester and say, oh my God, I don't even know where to start. I don't have all the information I need, and not be able to kind of work to what that information is that you need. So when you get a question like this, say, okay, I want to get the z-scores for all of this. Well, let me write down the equation for z-scores. Well, I know that I need the x value, and I know that I need the mean. I know that I need the standard deviation. All right, well, I've got the x values. The x are each one of these. I don't yet have the mean, so I'll need to find the mean for all of this. And I don't have the standard deviation. Well, do I have the variance? Nope, I don't have the variance. I need the variance. To get the variance, I need the sum of squares. Do I have the sum of squares? Nope, I don't have that either. So, working your way back up, knowing that the standard deviation is equal to the square root of the variance, which itself is equal to the sum of squares divided by n, right? And so that would be for the standard deviation to get the square root for the sum of squares of n. This is confusing. Just ignore this for a second. But you get the idea, right? So you've got what you need and figure out how to get what you need by working back up that ladder. All right, so when an entire distribution of x values is transformed into z-scores, the resulting distribution of z-scores will always have a mean of 0 and a standard deviation of 1. So that's kind of a good sanity check when you're doing practice problems or doing it on your exam. If you find the mean and the standard deviation of the z-scores, and they're not 0 and 1 respectively, you know you done did screwed up. So, just to serve another kind of framing of this, if we have our data up here, our raw data, such that we have 1, 0, 2 2s, 1, 3, 1, 5, 1, 6, we have our mean of 3, we have our standard deviation of what looks like 2. Transforming that into z-scores does not affect the frequency at each one of these points, right? It just changes what would be on this x, on the x label, or on the x-axis, rather. So you can see you've got one value that is at the mean, and you can see you've got one value that is at z-score equals 0. You have one score at a standard deviation above the mean, that 5 there, and one standard deviation equals a z-score of 1. See 1, see 2. Sounds like somebody's got music playing, so if you wouldn't mind either muting yourself or pausing that, that would be appreciated. Thank you. And so you can see 1 point lower than the mean here corresponds to 1/2 of the standard deviation. So negative 0.5 for the z-score. You still have 2 data points at that level. And so the advantage of standardizing these distributions is that you can make 2 or more distributions similar enough to compare. So for example, if one distribution has a mean of 100 and a standard deviation of 10, and another distribution has a mean of 40 and a standard deviation of 6, you cannot, in their raw form, necessarily compare those distributions. But what you can do is convert them to z-scores, or you can convert from z-score to now that new distribution, and we'll do an example of that in just a second. But converting them both to z-scores allows you to now have essentially a common language by which you can compare those values. This is just reiterating what I've already said. Again, the z-scores are completely standardizing everything, right? So you're always going to have a 0 for the mean, the z-scores, And a z-score of 1 means 1 standard deviation above. So you can see now how you're able to compare across different distributions. It's also possible to calculate z-scores for samples and not just populations. The equation is the same, it's just what are you putting in, all right? So the mean is the same, it's just represented by m, right? Rather than mu to denote that this is a sample. And then you have your S here, which designates this as the sample standard deviation rather than the population standard deviation. But the core of the equation hasn't changed, right? You still need a mean and you still need a standard deviation. So although you can transfer all of this into z-scores itself, a lot of people don't like it because they don't like dealing with negative numbers and decimal points, etc. And so you can create a simpler standardized distribution by selecting the mean and standard deviation that you would like for that new distribution, right? So you can take those raw scores for the IQ test we were talking about and say that we want a new mean of 100 and we want a new standard deviation of 15, right? So now we can take what may have been very noisy data before and transform it into a distribution that is a lot nicer and easier to interpret. You know, if you have an IQ of 130, you're 2 standard deviations above the mean, right? It becomes really easy to then interpret it. So then you're taking every z-score that you just calculated from that raw distribution, identifying the individual's position in the original distribution, right, through that z-score, and then you're computing the individual's new position by using that x equation, right? So you're taking x of that new mean that you want plus the z-score that you just calculated times that new standard deviation that you want. We're going to do an example of this in just a minute. So again, suppose, for example, that you want to standardize a distribution that has a new mean of 50 and a new standard deviation of 10. An individual with a z-score of -1 in the original distribution would now get a 40 on this new distribution. So it doesn't really matter what the person's score was before this. You can now get it such that they are operating around that standardized new distribution with that mean of 50. Further just iteration, reiteration of what I've already said. All right. So let's say you've got a population with scores that have a mean of 27 and a standard deviation of 4. So that's what you have over here. You have your mean 27, your standard deviation of 4. And from that, you want to create a new population from those scores that have a mean of 50 and a standard deviation of 10. So based off of that, what are we going to do to get these new scores? Yes, first find the z-score. All right, and so how do we find the z-score again? Mean over standard deviation, exactly. So for 19, you're taking 19 minus 27 over 4. So that gives you -8 over 4. So that gives you a z-score. I'm going to write them off to the right here. So that gives you a z-score of -2. We're going to take 25 minus 27 over 4. That gives us negative 2 over 4, or negative 0.5. 31 minus 27 over 4 gives us 4 over 4. So that gives us a z-score of 1. And then 33 minus 27 over 4 gives us 6 over 4, or 1.5. Right? You can quickly do a quick sanity check to make sure that you did everything correctly. If you just add up all these z-scores, negative 2 plus negative 0.5 is negative 2.5 plus 1 is negative 1.5 plus 1.5 is 0, right? So we know we did everything right. Or at least we screwed up in a systematic way. All right, so now we've got the z-scores for each one of them. What do we do to get the new values? Yeah. And what is that equation again? Either way, I mean, you're multiplying it. So yeah, so mean plus the standard deviation times that z-score, right? And for the new, we want that new population to have a mean of 50 and a standard deviation of 10. So for each one of these scores, we're just going to plug those new desired values into this equation. So our new x is going to be 50 plus 10 times negative 2, or 50 plus negative 30, or 50 minus 30, 50 minus 20, which gives us 30. We can do that for the next one. So we have 50 plus 10 times negative 0.5, or 50 minus 5 gives us 45. Same with 31, 50 plus 10 times 1, or 50 plus 10 is 60. And then 50 plus 10 times 1.5, or 50 plus 15 gives us 65. Right? And so now we can do another sanity check, make sure we did everything right by finding the mean here. So if we have, let's see, 30, 75, 135, 200, 200 divided by 4 gives us 50. Perfect. Did it all right. So you can see how we created brand new values, brand new x's for this that gave us exactly what we wanted, right? We wanted that mean of 50. We wanted that standard deviation of 10 because now it's just so much easier. If I say you have a score of 60, we know you're one standard deviation above the mean, which is a lot easier than saying, okay, you've got a score of 31. What are you, right? That takes a lot more mental calculation. Questions about that? Yeah. Possibly. I don't know. So are you interested in, like, you're essentially saying if we want that new population to have a mean of 80 rather than 70, yeah, what you would do?
When developers were explaining, it was always taking the curve test scores with 75 being the
Yeah.
80.
Yeah, so that's one of the ways you would do it. Yeah. Yeah. How would I check to make sure I did it right? So I would just find the average of these new values and make sure that that mean corresponds to my desired mean. So when I added all them up, I got 200 divided by 4 gives me 50, which is what I'm looking for. Make sense? Cool. Any other questions? Awesome. So when we look at that, those are in fact the new values that we got. Easy peasy. All right, so now we can go back to that question we started the class with. Average snowfall in Caribou, Maine is 110 inches with a standard deviation of 30. In Boston, Massachusetts, it's 24 with a standard deviation of 5. Last year, Caribou got 125 inches and Boston got 39. In what city was winter much worse than baseline, or much worse than average? So go ahead and spend a couple minutes and try to figure this one out, and then we will bring it together. So what would your X be in this case? So you've got, you have your mean, right? From what the average snowfall is, what you have your standard deviation. And you're trying to see if that new value from last year is significantly worse in Boston or Caribou. And so X in this case would be that new value. So that snowfall, which last year in Caribou was 125 and in Boston was 39. Excuse me. Does that make sense? If not, you're allowed to say so. No? Okay.
So would it be that 125 minus 110 over 30? That's my question.
That sounds right. I don't remember the exact numbers here. So, yes.
Okay.
Yep.
Okay.
27 more seconds. All right. What do we do? Yeah. Exactly. Yeah. So let's do for Caribou with a C and Boston with a B. So average for Caribou is 110 inches. Standard deviation is 30 inches. Boston, mean is 24 inches. And the standard deviation is 5 inches. So to find the z-score, we're going to take the new value, or in this case our x, which is 125, 25 minus 110 divided by 30. And that gives us 15 over 30.5. And then for Boston, we have our new x value, which is 39. So to get our z-score, we take 39 minus 24 divided by 5. So that gives us 15 over 5, or 3. So based off of this, what's your interpretation? Did Boston or Caribou have a worse winter than average? Boston, yes, exactly. In fact, it was 3 standard deviations worse, right? So even though you had 15 inches over average in both cities, because you have a smaller standard deviation here, right down there, it was substantially worse in Boston. Now, I know you may be asking, okay, why does the standard deviation have anything to play in there? Shouldn't it just be the mean, right? So now we're going to be thinking again about these normal distributions, right? If you have one distribution that looks like that, and another distribution, oh God, that's awful. Pretend that's not normally distributed. Stop laughing. I'm going to fail all of you. Just kidding, I'm not going to fail. Jesus, that looks so bad. So you have 2 different variabilities here, right? It is a lot less likely in this smaller, perfectly drawn normal distribution here that you would get something 15 inches above that mean than in the bigger Caribou distribution back here, getting something out here, right? Because if this is frequency on the y-axis, you have many more people at that 15 with that Caribou distribution than the Boston distribution. Does that make sense? Cool. And this is the underpinning for everything else we're going to be doing with the means testing this semester, right? You're going to be looking at the differences as a function of the variability, the variance. You'll do it in different ways for different tests. But if you feel good and comfortable with this, you should be feeling good and comfortable moving forward, because this is the same kind of theoretical foundation upon which we're going to build every other test this semester. Questions about what we covered today? Oh, one from Jay. Just to clarify, do z-scores only work for symmetrical distributions and not skewed ones? So they do. I mean, you could still find the z-scores for skewed distributions, but you start violating kind of some assumptions. And so for this class, you're not going to have to worry about it. That kind of stuff will be covered, I think, a little bit more in the standardization of asymmetrical distributions and higher level stats. But for this class, you'll just be doing it on normal distributions or symmetrical distributions. Other questions? Yeah. I don't remember what I said on the syllabus. Do any of y'all have the syllabus?
We're not gonna have like a study guide.
Okay, yeah. So I think we have a specific review day on the class before the exam day. Yes. Yep. Other questions?
So I can figure it out and I put the scores for one city here and then this for
Awesome. Yeah.
because it's a little bit harder for me to do it in that way where I overlap 2 curves.
Mm-hmm. Yeah. No, I mean that's great. You're just graphing it yeah, exactly right.
Will we ever be asked to do charting like either that way or this way or anything drawn out on the test?
Probably not in that form. Yeah. Canvas makes it next to impossible to actually draw things on the exams. So I'm trying to figure out if there are creative ways around it to allow know, to do a little bit of stuff like that, but I haven't figured it out yet. So it'll mostly, I mean, you'll be able to have scrap paper, and so you can do it like that.
Yeah.
But probably won't turn in an answer that looks like that. Any other questions? Comments, concerns, declarations, fears, hopes, aspirations? Awesome. Well, stick around if y'all have any questions. Otherwise, have a lovely weekend, and we'll see y'all next week.
Excuse me.
Yes.
Could you go over the graph stuff you said about the new standard deviation and the like with the snowfall and stuff? Because I didn't get the explanation from the graph.
Say that one more time. The graph about what?
About the snowfall in Caribou and Boston.
Oh, okay. The last graphs I just drew.
Yeah.
Okay. Yeah, absolutely. So I'm going to go ahead and make this again. So you have a distribution for Caribou that we'll say looks like this. So this is our Caribou distribution. And you have another distribution that looks like this for Boston. All right. And so you've got your means, and then you have your standard deviations. All right. And so this represents one standard deviation above. Here, you've got one standard deviation above. And so when you're looking at that standard deviation, you're getting a wider standard deviation here for Caribou than you have for Boston. And so if I say, okay, what is 15 inches of snow greater in Caribou equivalent to, you can see out here, 15 inches, an increase in 15 inches corresponds to a higher frequency, right? There are more people here above that. You go 15 out here, and you go above that x-axis there. And so what this is saying is that the proportion, or the probability that you get 15 inches more in Caribou is more likely just because you've got a larger spread of this distribution than you have here for Boston. Does that make sense?
Yeah, but you did say that the snowfall was worse in Boston. Or was that mean it was worse in Caribou?
No, it's worse in Boston because getting 15 inches more here means that it is a lot less likely to be due by chance, right? And so when we're talking about the equation, you're dividing by the standard deviation. And so in this case, the standard deviation is telling you essentially, does that 15 inches, is that more likely when you've got a wide distribution like this, or is it more likely when you've got a narrow distribution like this? And it's a lot more likely when you've got a wide distribution like this than when you've got a narrow distribution. And so if you are looking at that standard deviation, the fact that you have to go up essentially 3 standard deviations for Boston means the probability here of actually getting that just by chance is a lot lower, and therefore you have a, it is worse in comparison to Caribou. Does that help?
Maybe not really, but I think maybe I should do office hours or something because I'm not really getting it. I
Okay,
was also
yeah,
gonna
why don't you
ask.
shoot me an email and we can do a Zoom meeting.
Okay. I was going to ask about the stuff you
I'm
said
sorry, you said?
that the stuff you were saying about the z-score having to be 0 and the mean having to be 1 or something like that, like, and that means it's standardized.
Mm-hmm.
I didn't get that.
Yes. So when you create a z-score distribution like we did in class, that example, the average of those z-scores will always be 0, and they will always have a standard deviation of 1. So when you go back to your example that we used in class, if you worked all of those out, let me actually share here. So when you work out all of these, because we created our new z distribution here, the average of all of these, if you add all of them up and divide them by the number, you get 0. Although if you add all of them up, you're going to get 0 anyways. And the standard deviation, if you were to calculate the standard deviation of this distribution here, that would always come out to 1. That's just what happens when you standardize with z-scores.
Okay, thank you.
That makes sense?
Email you.
Yeah,
I'll
absolutely.
email you about the stars. Thank you.